All right, so first, thank you all, the presenters and also the guests for coming. And now I will continue with the presentations. I will follow the Machian presentations. I will try to link it to the problem of dark matter in galaxies. And I will first start with the observations of dark matter in galaxies. Now we'll talk a little bit about MOND, about modified Newtonian dynamics. I hope you have heard about it. And then I will try to talk about what has to do with Mach's principle. My paper is available in arXiv for free. So first, I'd like to start with the observations. We observe the visible mass of these galaxies, of their stars, the gas and dust, measured by mass-luminosity relationships and emission lines, and rotational orbital velocities through the Doppler shift. And with right now the data we have, for many decades, we can actually find the regularities and patterns in dark matter in galaxies. So we have a lot of data. This is the opposite to the problem of dark energy, where it's very difficult to attack. We don't have patterns and regularities and things like this. I will explain a little bit the main observations related to them. So first, in the galaxies, I'm going to just talk about galaxies at the beginning. The tangential velocities are asymptotically constant, asymptotically flat when you go far away from the center, while Newtonian gravity predicts a Keplerian fall-off, and it also makes a lot of sense that the outer parts of the galaxy should rotate much slower than the center. Then we have this very interesting observation that the values for these asymptotic flat velocities, the value of the velocity, are proportional to the fourth root of their visible mass. This is the active gravitational mass of the galaxy. This is also an observation. It's called the Tully-Fisher law. Also, you get that features in visible mass strongly correlate with features in velocity profiles. This shouldn't be expected, or at least you shouldn't expect such a correlation with physical cold dark matter. When I talk about dark matter, I'm going to call it the effect, the observational effect. And when I say physical dark matter, I'm going to talk about the cold dark matter hypothesis, the mainstream idea. And this is very interesting. You also have the notion that Newtonian gravity correctly predicts the velocity profiles at the cores. So Newton's laws work. This is very general, but it works generally at the cores of galaxies. And you also only get this difference in observed velocities with Newton and what you expect from Newton and what you observe at the edges of the galaxies, far away from the cores. I will talk about velocity discrepancies or mass discrepancies. They are basically the same concept. By the way, stop me anytime you want for making questions. And I didn't come up with this name, but they call these kinds of things the new Kepler laws for galaxies and for galaxy dynamics. They are not easily explained by dark matter. And this is very important because you will think, oh, okay, let's try to modify gravity or let's try to modify inertia to fit these dynamics of the galaxy. The easiest way to do it would be to change how gravity or inertia behaves at a particular distance scale, but you cannot do that. You cannot fit a law of gravity which changes at a particular distance scale for all the galaxies. Why is that? Because it's related to an acceleration scale, not a distance scale and not a mass scale. This is typical, very good example of a galaxy rotation curve. You've got distance from the core at the x-axis in kiloparsecs and velocities in the y-axis. The points are the measured values. The dashed line would be the Keplerian fall-off, so what you expect from Newton's laws, to apply Newton's laws. The points are gas, the contribution to the velocities from the gas of the galaxy. And in case you're wondering, then the line fitting the data is MOND. I will explain MOND later. And when you try to this is for different galaxies, when you try to plot this is the discrepancies in velocities. So you are plotting on the y-axis the observed velocity against the expected from Newton. In terms of radius, you don't find a correlation. That's why you cannot fit a particular, you cannot fit a scale of distance and try to solve all the galaxy's dynamics with that. But when you plot it against accelerations, you do get a correlation. So this has something to do with accelerations. with a particular acceleration scale. And you can see, as I said before here, that actually Newton's laws work more or less usually, yeah.
Acceleration of what?
Measured acceleration.
Of what?
Of the stars around the galaxy.
Towards the center.
Orbital.
Oh. Okay. Centrifugal. Oh, towards the, centripetal, towards the center. Okay. Yeah. Yeah.
So Newton's laws work usually at the cores, and you start to get these velocity discrepancies at a particular acceleration scale. People have measured this, they measured it, and they surprisingly, there's a value that fits all the galaxies. So you start to see the mass discrepancy at a particular acceleration scale takes the value of 10 to the power minus 10 meters divided by second square, more or less. Again, this works for all the galaxies. And with this, you may say, okay, let's try to modify Newton's law of gravity or the Newtonian inertia based on an acceleration scale. What you would arrive if you try to do that in the simplest way is Milgrom's MOND. It was developed in 1983 by Mordechai Milgrom. It's been over 40 years. And you can think about MOND as either a modification to gravity or modification of inertia to the second law of inertia. What you are basically putting into the law is an interpolating function mu, which will depend on your acceleration scale that we saw before and through acceleration. The interpolating function, depending on where you move it, it will be modified gravity or you modified inertia. It has to satisfy these two conservations, these two conditions. I don't know if it's too small. But, it needs the interpolating function needs to reduce to unity to recover Newtonian laws. So you want to get that the function goes to 1 at the high accelerations, so at the cores of galaxies, in the solar system, blah, blah. And then the second condition is basically to satisfy the Tully-Fisher law, that is the fact that the observed velocities are proportional to the fourth root of their visible mass. When you try to do that, this is the acceleration scale, data-fitted acceleration scale. What you get is the flat velocities that we saw take this value. You see there's the fourth root of the visible mass, and then there's a gravitational constant and your acceleration constant. You need that for dimensional analysis reasons also. And above this acceleration scale, you get the usual Newtonian. So this works for the solar system, and it works for galaxies also, without the need of physical dark matter. Milgrom has a preference for modified inertia, although most of people working in MOND work as modified gravity. I would say 90% prefer to modify gravity. The way I think about MOND is kind of like an empirical formula. It really comes directly from observations, all right? So it's literally meant to satisfy observations. That's why it works, and it works very well. Indeed, well, when you take the limit of this new fundamental constant that you need to introduce, this acceleration scale, to zero, you also recover Newtonian gravity or mechanics. And people criticize MOND saying it's data fitting. Well, I would go beyond that and say it's literally a law built to satisfy the observations, like the simplest way you could do it. The thing is that, as far as I know, in the people working on physical dark matter, the way you work is that you observe a new galaxy with a mass density profile, and you go to your library of dark matter halos. You pick the one that fits better your galaxy. Depends on the size, and your galaxy has a size and so on. You distribute this physical dark matter as you want with some parameters, and then when it works, and you can get your galaxy rotation curves, gone, perfect. With MOND, you give me the mass distribution, I'll get you the rotation curve directly, just with this constant over here as a free parameter. It's a single free parameter.
But the parameter is different for every different galaxy?
No. I just said they're all the same.
Okay, great, yeah.
Fundamental question is why modifying gravity? Wouldn't it have been sort of neater to just say, okay, instead of making gravity more complicated, just overlay another force on top of it and say, you know, gravity stays, and then on top of that, here's another force that is just weaker, which we only notice, you know, at those sort of scales?
Well, you have these hints from the observations I just said that are very difficult to explain with the alternative cold dark matter mainstream idea of having physical dark matter. So there's some hints like there's an acceleration scale. This is an empirical fact that you observe that. So yeah.
The point is also that it's a mass interaction. It's an interaction between masses, and so it
Feels like it belongs to gravity.
Yeah. But you could probably interpret it as a separate thing, but that might be superfluous.
Because it has to do with masses interacting with other masses.
That's why they're stuck in with gravity.
Yeah.
How precise is A0? Is it order of magnitude? Is it?
This is the value people use to
Yes, but
work.
is it plus or minus 0.1, plus or minus 0.1000, plus or minus 5?
You're not going to have huge precision for.
Yeah.
Not in the galaxy rotation curves. Like the galaxy rotation curves are not very precise.
What strikes me immediately, what probably most people wouldn't recognize, this value, 1.2, but without seconds, just 1.2 10 to the minus 10 meters, is more or less the diameter of the hydrogen atom.
We will go into coincidences later.
Okay.
All right?
Why?
We will go into coincidences later. So people say it's data fitting, but you choose which model or way of working you think is more data fitting.
And with dark matter, they have to choose a different dark matter distribution for different galaxies.
Yeah, they are very small and very big. The dark matter helios for some will be very small, for some galaxies will be very big. Yeah, and you need to distribute it correctly, and you need to make sure it doesn't clump at the cores, because otherwise Newton's laws shouldn't work at the cores with parameters.
And there's no common rule of distribution that applies
Excuse me,
to
I
all the
would rather
galaxies.
like to hear a talk rather than a random conversation.
I like it. I like it. No, I like it. I like it. It's fine. So the key question is, why does MOND work so well? Because it's a stupid equation.
Yeah.
If you have ever heard about MOND, it is because of how good it works. I'm not going to explain why. I'm not going to show you how many galaxies you can explain very easily. But if you have heard about it, it is because it works extremely well. And the question is, why and where does the interpolating function come from? No one knows. So I will go very quickly through what's done in MOND after 1983. Of course, people complain to Milgram, hey, this doesn't conserve momentum. You need to derive it from a Lagrangian. This is most of the work is done as modified gravity. You introduce the interpolating function into the Poisson equation. You can get conservation laws out of it. And then due to pressure of the community saying, oh, no, it's not relativistic, blah, blah, at the end, someone had to do the job and come up with a relativistic theory which reduces to MOND. The one who did it was Jacob Bekenstein. You may know him for the entropy of black holes. And, well, the theory he reaches is Tebes, tensor vector scalar theory. It's very awful because for every field you need to introduce, you introduce a tensor field, a vector field, a scalar field and a vector field. For every field you introduce, you also introduce new free parameters. So you break with the elegance and the simplicity of MOND since the very beginning. Even Milgram, I believe, he doesn't think this is the final theory or anything. But it does reduce to MOND, and you get also gravitational lensing, which is an observation of related to dark matter. You observe too much gravitational lensing. So thankfully, people have already explained Mach's principle before. I don't have to go through it. But very quickly, Mach conceived inertia as an interaction that required other external bodies to manifest. And the inertia of a body is not an independent and intrinsic property of matter. It arises from the interaction of the rest of the masses of the universe. This will be very important. You should also expect the non-absolute elements and dimensionless ratios for observables related to relational mechanics. And I want to talk, this is very important. So Einstein, after publishing his field equations in 1922, I think, although here it says 1921, he expected general relativity to be a fully Machian theory. He expected to satisfy Mach's principle completely because he thought by using tensors you could do it. Dalet has shown that This is not a good reasoning. You can also reformulate Newtonian gravity in tensor forms. It doesn't mean anything. It doesn't change the physical meaning. But Einstein quoted or listed 3 consequences that a fully Machian theory should satisfy. Apparently, general relativity satisfies 2 of them. The one you're seeing here is the one that it doesn't satisfy. So that's why people concluded very early that general relativity is not Machian. It doesn't satisfy what you should, or you don't get what you expect from Mach's principle in total, like all the full Mach's principle theory. What Einstein said here is that the consequences, or what you should expect from Mach's principle, is that the inertia of a body must increase when ponderable masses are piled up in this neighborhood. You can rephrase it the other way and say that when you remove a mass from neighboring masses, the inertia should decrease, and you can go to the extreme and say in the empty universe there should be no inertia. If you're curious about the other 2 that are satisfied in general relativity, we have talked about this with Dennis. One of them is that you get a shell mass of mass m, you rotate it, you are inducing inertial forces inside. This is due to frame dragging. You're literally frame dragging with the shell mass. And the other one is when you have a body and a group of masses and you accelerate these masses, then you induce acceleration in the same direction in the other body. This is also satisfied in general relativity by frame dragging, but this is not. This is clearly is not. So what the Milgram said about Mach's principle and MOND is very little. He just found 3 quotes of him. Very quickly, he says that an attractive possibility is that MOND results as a non-relativistic, small-scale expression of a fundamental theory by which inertia is a vestige of the interaction of a body with the rest of the universe in the spirit of Mach's principle. And he also said somewhere else, it has been long suspected that local dynamics is strongly influenced by the universe at large, a la Mach's principle, but MOND seems to be the first to supply a concrete evidence for such a connection. He didn't go further anything else. He didn't develop it further, I think, after correspondence with Milgram. I think he was biased on Mach's principle because he thought he necessarily resulted in the anisotropy of inertia, which already Dennis has said very briefly is ruled out by experiment, but it's not necessarily the case. Before. So Milgram finds very quickly that his acceleration scale coincides with c squared on the square root of the cosmological constant. All right? And I first was studying MOND, and then when I found out about Mach's principle, either by Dialec's videos or Alexander's videos, what I knew is that the cosmological constant, you can put it in terms of the energy density of the vacuum. This is the energy density of dark energy. And because of working in dark energy, I knew that this has the same orders of magnitude as the energy density of matter. So you can actually put the acceleration constant in terms of the mass and size of the universe. When you do this and you take also the Hoffman-Reisner-Schrödinger-Sciama's equation that we have talked before, we need to come up with a better name because this is horrible. For the gravitational constant, you got this coincidence from the talks you have already seen before, and you got this one, new one, from all the reasoning that I went, but you can see it without.
5 other names you could add to that.
They should be the ones who came up with it independently, but when you do this, you can just plug in this back to the MOND equations. I know this looks very messy, but basically what I have done is substitutions, and the results are the same, or at least should be very, very, very similar. I wrote the important result is that you end up with the inertial law, so a second law of inertia that depends on the global mass distributions, on your local mass distributions, that would be the mass of the galaxy, the field intensity of the galaxy, and the inertial mass of a body. So you've got an inertial law which depends on all the mass distributions playing a role into the dynamics.
Let me make sure I get the big picture. So the big picture is that the stars that are on the edge of the galaxy are further away from the other masses, and as a result, their inertia is less, so they go faster than expected. Cool.
This would be this is already my work. Like, no, from here below, this is my work all and my interpretation. I'm not talking about Milgram's work or anything. But it would be that this removing of masses is quantitatively measured by field intensities. So when you go to low accelerations or low field intensities, which is the case on the outer parts of the galaxies, then you get a boost in inertia, a decrease in inertia, or a boost in gravity. One or the other. It's equivalent. But I like the modified inertia more. So the interpolating function looks like this, and you need to satisfy, again, the conditions before to get the usual Newtonian laws in the solar system, which they work. The solar system is in the high acceleration regime. And so basically the field intensities are higher always than that of the ones you get from the mass and radius of the universe. So what is Mach and MOND? Well, we were already talking about this. The interpretation I do from Mach and MOND is that when the local field intensities is above that of the rest of the universe, so for instance in the solar system, because of the sun, you got very high field intensities. At the cores of galaxies or at the solar system, the mainframe acceleration is defined with respect to is the local one, and you can describe the dynamics of the system without referring to the field intensity of the universe at large through the usual Newtonian laws. But when you go to the place in which the field intensity of the rest of the universe is greater than that of the local system, which would be the case of the outer parts of the galaxy, then you would be in the deep MOND regime and the flat rotation part of the distant galaxies. It seems like acceleration is defined with respect to the background frame of the universe, and you need to take into account the field intensity of the universe at large, non-linearly, by the way, together that with the local frame to explain the dynamics of the local system. And yeah, in between both regimes, it is shared. So the interpolating function basically it's called an interpolating function because it goes from the Newtonian regime to the low acceleration regime. Depending on the interpolating function you take, you get one slope or different kinds of slopes. That one is chosen arbitrarily, the type of the interpolating function. And this what looks like is that you're missing boundary conditions. So in general relativity, the local dynamics do not depend on the mass of the universe or the radius of the universe, because you always have, in the partial metric, flat asymptotic space at infinity. But Mach, the idea of Mach is that somehow global parameters affect local dynamics. This is what you get very clearly in Mach and MOND. So it looks like you're missing an effect from boundary conditions. So I'm going to argue, although the whole presentation is an argument for this, why MOND is Mach's principle. Well, first, you can reformulate it and works the same way with the mass and radius of the universe. These parameters appeared in all the Machian theories of unifying gravity and inertia. You get stronger nonlinear dependence of local dynamics on the global parameters through the field intensity, not the potentials, as you guys do, but also on the field intensities. You don't have fundamental constants except for the speed of light. And, well, I'm going to show you now the equations you get for the velocities. So what is the velocity at this flat velocity of the galaxies? What you get in the low acceleration regime is this formula for it. It's interesting because you're calculating velocities straight out of a factor of the speed of light. You can see here that you are still taking the fourth root of the active gravitational mass. This is the key point to satisfy the Tully-Fisher law. And the MOND equation is this one. So I went from this to this. Julian Barbour likes this a lot, the relational dimensionless ratios. That's the only thing he liked about my Mach and MOND. You can see that these velocities are independent of the radius. That's why you get a flat. Even if you go like far away from the galaxy, you get still the same velocities. That's how you get the flat rotation curves. Also, it's funny that it's independent of the radius of the universe. So And for high acceleration regime, you get these velocities. This is the Newtonian one. I think you get this also from Sciama's. Once you introduce the formula for the gravitational constant, you get this. But I have never seen it, I think. So.
Okay, we'll have to talk about it.
All right. And, well, you can think about, okay, what if I double the mass of the universe? Then I'm doubling also, I have to double the mass of the galaxies, so the velocities stay the same. You got some kind of scale invariance in mass, which is very interesting. You already got scale invariance in length. And even here, if you double the size of the universe, you also double in the size of the galaxy, and you get the scale invariance. This is already a feature of Sciama's theories. This is scale invariance, but it respects it because the interpolating function is again a ratio between field intensities, so you get the same effect. You respect that scale invariance. When you do the equation for the gravitational constant and reduce the mass of the universe, you still increase the gravitational force or decrease inertia. You respect this effect from Mach. You would expect with Mach, even with the interpolating function of Mach and MOND. And here I will quote a thought experiment from Alexander, but I think it's not original from Alexander. There's this effect by which, okay, let's take the mass of the universe and empty the universe and think that that's just the mass of the galaxy, all right? So you take mu, the mass of the universe, you put m, the active gravitational mass of the galaxy. You do the same for the radius. Turns out the interpolating function reduces to a simple number. It can be set to unity with the appropriate integrals, which are missing everywhere because, and for any mass or any radius, you get orbital velocities of the speed of light. You still get this in Mach and MOND, although it's already a feature of the Machian theories. So basically you're saying in absence of the rest of the mass of the universe, the velocities are around the order of magnitude of the speed of light. Why? Let's think about the thought experiment of Alexander. You have two masses in an empty universe. Let's assume they rotate around the center of mass, or I think it doesn't matter if one rotates around the other one. From a Machian point of view, it makes no sense to speak about rotation because there is not absolute space. The two masses define the inertial coordinate frame, so you cannot basically see if you are one of these masses that the other one is rotating. And mass 1 and mass 2 have a gauge freedom, choosing any rotating coordinate system up to a particular angular velocity corresponding to rotation of the speed of light. So you expect this from Mach, something like this already, to get the velocities of the speed of light when you empty the universe. So you would expect that now that this is because general relativity is not Machian. So if you could really make general relativity fully Machian, the hope is that you would get Machian MOND with it. But there's another way, there's another path to get it, because in case you haven't realized, the interpolating function is very similar to the Lorentz function. And what you do in special relativity is that you relativize velocities through the Lorentz correction factor, and you get the fraction of velocities. So MOND is very, very similar. There's a plus here, but if you take the minus, we are always missing here, I think. Then you can rewrite it. If you don't miss it, then it looks much more like a Lorentz correction factor. But because you have field intensities here, which are basically accelerations also, it looks like Mach and MOND comes from relativizing accelerations in terms of Mach's principle. This is very speculative. Lorentz invariance implies that the speed of light is constant in all inertial frames, and it seems that Mach and MOND implies that the total field intensity anywhere in the universe is always above that of the universe, because you always have the universe there, giving you a field intensity. So I had personal correspondence with Milgram. He told me he tried to get MOND out of transformation between accelerating frames. He devoted a lot of time into it and got nowhere. He got things written in some paper, but very, very little. But we know Milgram has not thought a lot about these topics of the relativity of inertia, relativity of acceleration, Mach's principle, having the mass of the take into account the mass of the universe, and so on. So I think there is still hope that you might find where does this come from, because this is the question: where does MOND come from? Why does it work so well, and where does the interpolating function come from? How much time do I have?
Oh, you have an hour left. So.
An hour left.
Half an hour.
Oh, okay. That's good. So I think it's a possible way to prove Mach's principle through a phenomenological explanation of MOND. There is a way. It's very related. You need to try to guess what it applies to, whether if it applies to inertia and as a correction to inertial mass, or to gravity, to the gravitational constant, or a change between the inverse square law of gravity to an inverse law of gravity. That's what you get in the low acceleration regime. Its origin, well, it must be nonlinear because MOND is nonlinear. Its external field effect makes it nonlinear. Your theories of unifying the inertia and gravity are all linear, as far as I know, but MOND already is nonlinear. So I don't think you can get MOND from Sciama or Trader, or this must come from somewhere else. Like gravito-electromagnetism, which is linear and not Lorentz invariant. So everybody believes the interpolating function just arises, it's an emergent simplification from a fundamental theory, okay? The same way you get Newton's law of gravity out of the Schwarzschild metric, although it's not written anywhere there, you should get MOND from a fundamental theory as an emergent simplification. But somehow the field intensity of the universe should still play a role in the fundamental theory that points towards Mach's principle. And maybe the solution is making general relativity more Machian. I wrote, by doing algebra, all the possible formulations of the interpolating function. These are the two types. They work more or less the same as good both, in case you have found this somewhere and you can reminds you about something in your own research. And now, because I have time, I will talk a little bit about clusters. These are galaxy clusters, not globular clusters, because one of the main critics against MOND is that it doesn't solve the need for dark matter in clusters. It does completely solve the need of dark matter in galaxies, but in clusters it falls short. You got a mass discrepancies. This depends on the distance from the center of the cluster, but you get more or less mass discrepancies of 7-to-1. When you use MOND, you get a mass discrepancy of 3-to-1 or 2-to-1. That means you need double the mass that you observe to explain the dynamics. So it's in the right direction, but it falls short. People have tried to tweak MOND into, okay, maybe we need to tweak it further so it fits the clusters. And in the same way, Milgram was the one who identified that the mass discrepancy in galaxies occur at a certain acceleration scale. It was Jacob Bekenstein who identified that the mass discrepancy in clusters, when using MOND, occurs at a certain potential scale. So it's a very different case. So you would expect from physical dark matter to clamp because it only interacts gravitationally. But if it did, you would have very high mass discrepancies, so velocity discrepancies at the cores of galaxies. You see them at the edges, so that means that physical dark matter, if it exists, it doesn't clump. You need to say that it's frictionless and blah, blah. In clusters, when you use MOND, it's the opposite. You find the mass discrepancies at the cores of the clusters. And because people in MOND are not dogmatic at all, some of them think that, okay, maybe there's a little bit of physical dark matter in clusters to explain this discrepancy, but then MOND is also correct, and it works in galaxies. And if you want to tweak MOND so it boosts gravity or decreases inertia in a potential scale, so let's say you want to tweak more MOND to explain galaxies completely without the need of any physical dark matter, what you need to be very careful. Well, I tried doing this for a year without success. You need to be very careful because you cannot just boost gravity in high potential scales. Then you would be boosting gravity, for instance, in neutron stars, in which their dynamics constrain a lot a possible modification to gravity there. So what you need to do is to boost gravity or decrease inertia in high potentials but in low accelerations, because clusters of galaxies are still, even at the cores, at low accelerations, but they have high potentials. They have higher potentials than the galaxies themselves. And if you want to do that, well, this is reasonable that there might be some dark matter hiding at the cores of the clusters in high potentials. A completely different case from the galaxies. If you want to do that, and you need to make some kind of a function on potentials, multiplying inside the interpolating function. Of course, if you want to do it the Machian way, you take the scale of the potential of the universe again. That scale doesn't work. You need to put some factor, big factor on top of it. This looks already ugly. That's why I didn't publish this. And you may think that this comes from another dimensionless ratio. For instance, looks like it works from velocities with respect to the mass of the universe, of the galaxies themselves in the cluster with respect to the universe and the speed of light. It looks very ugly. In fact, Bekenstein came to this exact same formulation, but not in the Machian way. So he introduces a new free parameter of velocities here and compares it to a potential scale. But I arrived independently to the same results of Bekenstein through the Machian reasoning, but it doesn't look nice. So, and well, thank you so much. I have my paper on arXiv. I don't know how I made it to arXiv, to be honest, but you got it for free over there to check it out. And also I will promote my own YouTube channel in which I try to explain Mach's principle step by step in several videos. First one about Mach's principle. I have one about MOND also, then another one about the relativity of acceleration and many other topics related to Mach's principle. But this is just to redirect traffic to my website there, in which my publications are there. Yeah, thank you very much.
So how about the next level? So after galaxies and clusters, the next thing is what, filaments or something like this? Does it fit there?
I haven't heard about what the mass discrepancy you get in higher scales. So I don't know about them. People talk a lot about the clusters because, in fact, I think it was the first detection of dark matter. It was first said, okay, there is mass discrepancy in clusters. And even the mass discrepancy in clusters was like 70 to 1 or some huge values. But I've never heard about even going to larger scales and finding out the mass discrepancies over there and the dynamics of larger scales.
Interesting for a principle that applies to everything instead of like looking at each level individually.
Clusters and then empty voids.
Yeah, the voids is also a topic.
Different thing.
Is the cluster discrepancy measurement based on gravitational lensing or based on?
I think it's both. You observe the lensing, but you also can measure the velocities of the galaxies in between.
So a very popular thing is to go like people, for example, try to do the simulations of galaxy formation, and they put dark matter all the time. So I was thinking, how about we try a simulation where we have a grid, and we put instead of having a single value for the MOND correction, we have the Mach and MOND correction at each point in the grid, and it varies slightly depending on the masses all around. Maybe this could help.
So you mean a varying acceleration scale?
Yes, I mean the transition is not at the same value everywhere. It depends actually on the distribution of mass. So if you have a big void, the value will be different than in the centers of the galaxies.
I can tell you that it looks like the acceleration scale grows with a scale. So if you boost the acceleration scale in clusters, you might solve the mass discrepancies in clusters. People have tried this. It's actually what I did. I boosted the acceleration scale in terms of potentials. That's what my last part was. And yeah, this is considered like maybe it's not a constant acceleration scale, but it varies potential or something else.
Are you interested in trying to make such a simulation? Do you consider it worthwhile to try?
I know the papers who have considered it and tried to do it, but I don't remember any simulations done by that.
Maybe best bet now is the Mach bullet cluster.
Sorry?
Bullet cluster.
The problem with the bullet cluster is also brought as a critic to MOND, but it's basically the same problem you've got already in clusters in general. I don't think there's a lot of debate on it. I don't want to go into it, but I don't think it's a very, very big problem. There's a lot of debate, a lot of confrontation between people in MOND saying it's not a very big problem for MOND for some reasons, and people saying that it directly proves the existence of physical dark matter.
Now we have a very powerful James Webb Space Telescope. Now, have anyone using this new telescope to revisit some of the old measurements, including maybe the galaxy rotation or the cluster of a galaxy, and look at whether our newer measurement will provide any correction for the older observations, so therefore the implication, no matter you're using dark matter or using this MOND, maybe the data, right there, because in the older day, we're limited by our observation tool. So now we have such a great improved observation tool. With the data, will provide any significant change?
So the new data, the experimentalists have done a very great job. They keep on doing progress, thankfully. We have new data, and this data, we can already compare it to MOND, to what MOND predicted. For instance, MOND favors early galaxy formation, and we observed now very recently. Also, MOND supports that the flat rotation curves extend very, very, very far away, and now we are able to measure the orbital velocities very, very far away, and it follows. It's okay with MOND. And then what you could do, people are trying to do recently, is trying to measure the galaxy rotation curves of very early galaxies in the age of the universe, and see if it is different. See if it's the acceleration scale is the same or not, so you can measure the galaxy rotation curves of very early galaxies in the universe. That's very, very interesting, yes.
So concerning the connection of Mach's principle to galaxy rotation curves, there's also this other hypothesis that's been suggested, I don't know how much you've looked into, of getting the galaxy rotation curves out of gravitomagnetism. So out of the velocity-dependent constant gravitational fields, like you have, for example, in Sciama's model and in these other inertial. So essentially frame dragging, right?
Yeah, I know you like the frame dragging approach to the problem. Yes.
The thing is, I haven't looked into the details very much at all.
Me neither, but I think it's so obvious that somebody should have already tried and see whether I don't think you need.
The effect is not large enough.
Yeah, I don't think you get enough. So the velocity discrepancies are huge.
I know that in general relativity the effect's not large enough, but I've seen
it is the same order of magnitude in gravity electromagnetism. Because linearized general relativity is basically gravi-electromagnetism, so it's the same terms, just a factor of 2 or so is different, and this doesn't really make a difference.
And one thing, in general relativity, the higher the masses, the more the frame dragging, so you would expect actually even more mass discrepancies at the cores of galaxies, where you have more masses. You would expect more frame dragging at the center, and you don't see that. That's my problem with frame dragging at this.
But I thought it was one our relation. So you would get more frame dragging, but it wouldn't be a dominant effect of the core, right? Because the dominant effect would be the scalar gravitation.
You tell me about it. We discuss it. I like discussing the idea.
And now that you're relating it to reduced inertia, you and I have been corresponding, and I've been looking for gravitational acceleration and frame dragging explanations. But now that I understand that reduced inertia of far from other matter is the best, that is compatible with a flowing space concept. Whereas I said a single sink in a universe would have no inertia, flowing space would go along with the 2 masses, possibly having speed of light rotation around each other because there's nothing to. Whereas, out on the edge of a galaxy, there is far less mass to kind of tether the motion of the outer stars. And just one other comment, it's amazing. I didn't see the scale of this MOND until I, looked at a lot of galaxy pictures and accelerations. It goes all the way out. I mean, very far from the visible galaxy. You can have a star that still has this high velocity.
We are getting to the point in which we are out of the dark matter halo already.
Yes.
with the flat rotation. Yes, I'm very interested in the sinks and of the flow in space, and maybe there's some way out of it.
Will be discussion. I'll be throwing ideas.
Yes.
This is the class.
What is your take then on the equivalence principle?
With the equivalence principle,
What is your take then on it with incorporating your findings?
I think you satisfy it locally, even with modified inertia, but maybe others could help me with that.
Okay, so the question is, do you think it's broken or is it like...
No, if you just modify gravity, it's not broken, certainly. I would only expect breaking with the equivalence principle in some form of modified inertia.
Okay, so both change the gravitational acceleration and the inertia or just the inertia?
You can think about it as modifying gravity or modifying inertia. Modifying gravity is changing from an inverse square law to an inverse law of the distance. And modifying inertia is another thing. I haven't looked much into the equivalence principle. I think you satisfy it locally, at least. Yes. But it's interesting also.
How about the gravitational lensing?
You need a relativistic theory to make predictions. That's why people came up with Tevez. It does okay, but it looks very bad.
Complicated.
Very complicated, yes.
So I think the most straightforward way to see how it might connect with Mach's principle is to look at the modified inertia equation and then compare this with the relative inertia Machian models, right? And see if there's like a slight modification which could lead to.
You're not going to get it out of a linear theory.
Yeah, but it could be a non-linear modification.
Yeah, that's what this is, but with field intensities. We are playing with field intensities, not the potentials. Yeah. That's what I want to do. Yeah.
Okay. Well, maybe we can look at it later.
Sure.
Any further questions? You walked way outside the lines, man.
I know.
All right. Thank you very much.